Okay. So, good evening, everybody. Welcome. My name is Nikola Jelić, and I will be your presenter for the evening. Let's slowly begin. I will present my own C++ library that deals with physical units. And the part 2 comes from the fact that the original one was developed more than 5 years ago, but it was presented 5 years ago. And it was under quite a bit of ignorance from my side for quite a few years until we got a situation that I can use it commercially again. And what do you know? Every single feature I said in the original version that is not so critical and not so necessary became critical and necessary. And as I developed something new and interesting, Ivan contacted me to maybe share with others, hence here I am. In short about me, as I already said, my name is Nikola Jelić. I'm an embedded systems engineer with some roughly 15 years of experience. I work in Culke Engineering. I studied computer science at the Faculty of Mathematics, University of Belgrade. I also have quite a diverse list of hobbies, maybe more after the actual presentation. I would also like to give thanks to two of my colleagues not present here today, Aleksandar Dakić for some very cool ideas about the design of C++, and Nemanja Đekić for the actual CI/CD integration that I was simply too ignorant and lazy to do. As already said, I'm an embedded engineer, which means I deal with the type of computers which is now the vast majority of computers of planet Earth, the ones in the elevators, in your refrigerator, in these screens, computer drivers, and as I like to joke, if you do not notice it, that's embedded device. In almost every single case, it deals with some sort of physical measurement and action. That would be pressure, luminosity, flow of liquids, mass, electrical current, etc., etc. Now, there are many challenges with the embedded field and dealing with the units. Some of them concerned with precision of measurement, and that is mostly the area of the sensor design. Speed of acquiring the measurements, and also the equidistance between the samples. Precision of calculations, where my colleagues from digital signal processing and numerical mathematics could give much better talks. And poor little consistency of units, which is actually the focus of mine. The reason why I'm only dealing with this one is because everything else is actually more or less solved. What I saw on many of the projects where I worked commercially is that we would usually mark the variables with various suffixes, such as mass underscore kilograms or grams, or pounds or ounces, wherever, volume in milliliters, liters, again ounces, and so on. But this is completely just for aesthetics. You can still add kilograms to liters. You can divide liters by volts, and nobody will blink an eye. Additionally, you can also deal with two different measurements that represent mass, but in different units. Be that in scale, like gram, kilogram, be that in a different system, like pound or ounce, or in the case of temperatures, which is one of my favorite, therefore the least favorite topic, you would deal with not only the scale, but also the offset between the different units. So Fahrenheit, Celsius, Kelvin, and everything else also have the different starting points, not only the scales. Now, we can create conversion functions for every single combination of every single unit conversion in our code by hand, which is, again, difficult and error-prone, and you need to remember to call it every single bloody time. And it would be really, really cool, to quote an ex-colleague of mine, if we can magically put that into a compiler. So the closest thing to writing a compiler that I know of are actually C++ templates, especially in modern versions. So the basis of the solution is in the International System of Units, or SI. Long story short, we had many, many different measurement systems across millennia, and a few centuries ago, some smart people sat down and said, okay, you know what, let's standardize everything. And now we have 7 basic units, and we can represent every single thing measurable with known physics with the combination of these 7. I have put an example of volts, which is actually kilogram meter square per second cubed ampere multiplied by ampere. And this is not so intuitive, especially to me, because I'm a mathematician by vocation, not a physicist, so this makes no sense to me, but it turns out to be true. And also, as I said, the non-SI units can be represented as derivatives of the SI units, and sometimes with additional calculation. For example, Fahrenheit is 9/5 of Kelvin minus yada yada. Two things here. The separation of these, of every single physical measurement into the 7 units of SI, I learned later is actually not completely true. You can have 2 types of energy which have completely the same signature, but they're not convertible one to the other. And this is a known problem in physics, but nobody gives a damn, so I didn't fix it. And the other thing which actually embedded engineers really like to do is to measure angles and rotations of motors, and angle is not a SI unit. Effectively, angle is a dimensionless value, which is one length divided by another length. And this is mathematically correct and completely useless. We actually want to do rotations per minute. We want to measure the concrete position, especially in robotics. So I actually followed my engineering part of brain and added an 8th SI dimension just for the library, and we will see it's actually extremely, extremely useful. So the projects I've been working on, which directly influenced this, there were 2 projects. One of them was dealing with heating and dispensing of water, effectively tea or coffee machine, and the other one controls an electrical engine. So the reason why I originally had to develop the whole thing, and that will probably cut the first and most obvious question, well, Nikola, why the hell didn't you use any of the well-known physical units libraries for C++? We couldn't. The project was in a very late stage, and for legal reasons, they couldn't introduce a single third-party library anymore. Hence, can you write one in less than a month, like some sort of a prototype just for us to get going? So that was a legal reason for me to write this, and now that it's being born, now it's used, so why not? We were dealing mostly with time, represented in hours, seconds, milliseconds, volumes, temperature, and then various things like frequency, flow, rotations in degrees or radians per second, and so on and so on. The idea was to have either 0 or extremely low runtime overhead, so nobody wants to have an invocation of an invocation of an invocation and so on. And the desire was not only to refactor the existing code, but also to prevent by design any code physical unit inconsistency error in the future. So we would like to have a compile time error if we ever add millivolt to a milliliter, and not to detect it very late in the production. The types of errors I usually saw was, and these were quite tricky, when you have something which is in milliseconds and you assign it to seconds. So a timeout of 10 milliseconds becomes a timeout of 10 seconds, which is completely different order of magnitude. And if you deal with heaters and stuff like that, now you're in a completely wrong physical state, and so on. What I had at my disposal was at that point only C++11. And for us in the embedded world, this is actually the norm. It's very rare that we ever have access to C++14 or, God forbid, 17. Anything beyond 17 is just science fiction, and I'll wait for a few more years to get there. I based a lot of the code around template programming and const-expr methods. I really like the suffix operators that create literal values of your custom types. And I made a heavy use of STD ratio in several places. You will see that. Another thing I picked up from the STD chrono library, which is actually a huge inspiration, so can we do STD chrono but for everything, was the distinction between an absolute value, in case of chrono that will be a timestamp, and an interval. And turns out that other physical units actually want to have this as well. So let's go step by step. I will now guide you through a very cut and dry overview of the implementation, and we will discuss the solution later on. So the basic physical unit has too many arguments, but a majority of them are not so important. The last 8 are just the dimensions. Okay, so what's the degree of length, of mass, and so on? Is it meter squared per second squared, and so on and so on? The first few are interesting. Value type, very important for us in embedded. We cannot just put long double on everything. In many cases, we deal with microcontrollers that are still 32-bit without any floating point coprocessor. So we cannot pay 100 cycles for every multiplication and every division ever. So for many values, we really want to use integers, preferably 32-bit or smaller, and val type is just for that, for a Holder value. Conversion factor, we will use this, for example, if meter is the base SI unit, then the millimeter would be 1/1000 ratio represented here. So we don't have to remember 0.00, we just effectively move the floating point. Everything else, as I said, are just standard dimensions. Angles are added here as an 8th dimension, and we will have a separate subchapter just about the angles because they really act strangely compared to everything else, given the fact that when you move in one direction or when you heat temperature up, everything is fine, but with angles you can also end up in the same place where you originally were, which is an interesting behavior for the library. One of the most commonly used conversion operator was actually implemented by a conversion constructor. The idea is that the only 2 things that can differ when we convert from one physical unit to another are the value type and the factor. You can never ever convert seconds to meters or anything like that. So the conversion can only be done between the values that have the same signature, and it can only be done explicitly. We wanted to remove any chance of somebody accidentally moving from meters to millimeters or the other way around, especially since we mostly deal with integral values. Therefore, you can actually lose a lot of precision. So if you have 300 milliseconds accidentally cast to seconds, you get 0 seconds. That's it. You lose the entire value. So if somebody wants to do that, we wanted it to be explicit. All comparisons are done as you can imagine, honestly, if we had a spaceship operator, that would be much easier and nicer. We also can only compare things that have the same dimensionality and the same factor. Only the value type can be different. For example, if you have a 32 or 16-bit integer, but they represent the same value, comparison will be fine. Weirdly enough, I even tried to use complex numbers, and this is something that people in electronics like to do, and this works, as long as you do not compare it, is it something bigger or smaller, but actually the library works with complex numbers as well. Addition, subtraction, again, the same thing. The dimensions and conversion factors have to be aligned, and in all of these cases, the variadic templates are extremely useful. You just put 3 dots, and the compiler will chew what it has to chew. All of this, for now, is extremely trivial. The interesting things come in when we start multiplying and dividing physical units, because now we can create new unit types. If I divide the length by time, I have velocity all of a sudden. If I multiply frequency with time, I have a dimensionless value, and so on and so on. So how to deal with that? So the simplest of all cases, let's multiply a physical unit with a scalar. That's extremely simple. We just return the same type, but we multiply the value. Okay? That's extremely simple. Version 2, not so simple. Let's divide the scalar by a physical unit. And now we enter interesting territory. If we had, if we divide a number with 2 seconds, all of a sudden we are now in the frequency range. It's not a second anymore, now we have effectively hertz. So for me, interesting pieces here are that we will infer the type for the division. If we divide float by an integer, it will be a float, and so forth and so forth. The ratio is now the inverse, the factor is now the inverse of the original. But the cool thing is that for all the dimensions that our unit had, we can just now go and subtract from 0 every single dimension we had, and the 3-dot operator will do that for all dimensions in a row in one fell swoop. So this is quite nice. And the option 3 is when we actually, for example, in this case, multiply, but the similar thing would happen with a division, 2 physical units. And now we have a slightly more complex but quite similar situation to what we had before. We would multiply the 2 factors. We would multiply the 2 factors, and we would add, in this case, all the dimensions. So if we multiply length by length, now it's meter squared or whatever. So looks complex, not so much if you decompose it, like go from the simplest to a more complex situations, but fortunately we had all of these in the code. Another weird request I got is that, let's say you multiply seconds with hertz and so on, and now you get a dimensionless value. One of the silly requests was that I just want to get now the raw value out with the conversion factor factored in, and I created a template specialization that deals with physical units that have all dimensions 0. Simply put, you can only call this if your template actually has no dimensions left. So it's, honestly, I would never design something like that, but I had a cool colleague who said it would make his life easier because he was just working mostly with dimensional stuff. The last interesting piece, and that I would, yes, introduced in this section are the absolute physical units. And the best examples I have are temperature and time. So for length, it's not quite obvious what's the absolute length. We would usually just deal with intervals. But in time, I have now as today, even though we cannot agree what's the original measuring point. Is it the Unix epoch? Is it the Christian era? Is it Muslim era? Is it the age of the universe? We are quite imprecise there. And also, it's very difficult to multiply now by 2. But the time interval of 10 seconds, I can multiply by 2, I can divide by 2, I can do whatever. And also, if I have a time point, I can add and subtract intervals from it and get another time point. It's quite similar with the temperatures, and this is what we had with the heaters. Celsius and Kelvin have the same step. So the conversion factor, if you have heat this something by 10 Kelvin or by 10 Celsius, is completely the same. Only when I get to the absolute measured temperature, you all of a sudden see the big difference. So this was inspired mostly how STD Chrono did it. And we will now go into, unfortunately, I flipped through slides, so just ignore that. Let's go into the absolute physical unit, the basic type. It looked pretty much the same as the normal one, save the angles. Angles were intentionally left out because absolute units that deal with angles, such as direction, are specialized later on. We have an additional thing. We have 2 additional things here, and these would be the difference type, again an embedded thingy, and an offset. Offset is quite easy to understand when you deal with temperatures because Fahrenheit is weird. And also when you deal from Celsius to Kelvin, again, you need to add an offset. As I said, when you deal with intervals, you know, if you go from a foot to a yard or to an inch or a millimeter or meter, there is no offset. But here we deal with that. Diff type was actually, again, a project requirement. Milliseconds since the beginning of the epoch are always calculated as a 64-bit integers on a 32-bit architecture. Therefore, we really lose a lot of cycles. But all the differences were in the order of 1 integer. So when I do the calculations to an actual interval type, please cast back to a smaller one. So this is just like a bonus type for the cool people that have normal computers and will just use the long doubles everywhere. This is just one extra parameter. Okay. Conversion constructor is richer, and it took me a while to get it right, and I mostly tested it on various temperature scales. So from Kelvin to Celsius, Celsius to Fahrenheit, Fahrenheit back to Kelvin, and so on and so forth. The only complexity added here is dealing with the offset and with the factor all at once. Now, cool thing here, if any one of you didn't use the STD ratio before, it's a rational number compile time library in C++ templates. And for these sort of things, it's a godsend. Okay? And now, as I said, when you subtract 2 absolute units of the same type, you now get the interval unit, which shares the type completely in the sense of the signature, loses the offset, and it's now in the diff value type. It's quite easy. When you add interval unit to an absolute, you get a new absolute unit. Quite simple. So it's a lot of repetitive code. And the cool thing, and this is really improving readability, you can create your own suffixes. So in this case, for example, _L is for liters. And liters, weirdly enough, are 1,000th of a meter cubed. That can be confusing, but it's actually true. And you can create two operators such as this. In our case, they were actually using floats because they wanted to catch from milliliter to liter. A benefit of this is that, specifically in our code, I would say that 80% of all units were actually compile time constants because they were specific to a given heater, specific to a given pump, and so on and so on. And if you want to calculate some conversion factor between how much power you need to heat something up, 80% of these calculations can happen in compile time because this is now a compile time thing, this unit. Multiplying two constants in this thing is also a compile time thing, so you can actually save a lot of runtime cycles just by using this. Now, I'll go to the angles and to some interesting mathematical functions I had to introduce. And this, we are now past half of the presentation. As already said, mathematically and strictly physically speaking, angles are not a dimension. Engineeringly speaking, that's completely useless, and it should be treated as a dimension because in 99% of cases, it is effectively a dimension. Or as I like to quote one weird guy, 99% of the time, Earth is actually flat. For all intents and purposes, engineeringly speaking, we treat it as flat. And then when we reach a particular point, we actually notice something's wrong. And for embedded purposes, this is absolutely an SI unit. To my chagrin, we again have the unbound angle. So for example, 70,000 rotations, and then you have angles, God knows how many times wrapped around, then you need to calculate how many full circles happened. And there is a direction angle, which needs to wrap up back to zero when you rotate the full circle, which is effectively a really weird absolute unit again, but just in the area of angles. We also noticed some other things. Bound angles can be multiplied and divided. The directions actually not. You actually just measure the direction, and when you want to move from one piece to the other, you add something or retract something from it. The one weird thing is that the angle is not only normalized from 0 to 360, it can also be normalized from -half to a +half. And thankfully, those were the only two angle normalizations I had to deal with. I didn't put, another thing immediately on top of that was, yeah, that's all cool and great. I also took the degree, standard 1 degree, of which 360 fill in an angle because I'm an embedded guy and I like integral numbers. The problem is that every single trigonometry function, and lo and behold, people want to use trigonometry function on the angles, is written to use radians. And these are dastardly floating doublish values, and what to do with those. Turned out, it's not the problem to do the conversion, at least for the client in this case, because they will pay for sine, cosine functions anyway. The problem is how to create sine, cosine, tangent, arccosinus, also sinus, hyperbolic, and so on, all of these functions for all the physical angles ever. And I'm an extremely lazy engineer, so I created a template, and on top of that, I created a macro. So the 3 macros you can see, and there are 3 more for the normal angle unit, not just the absolute unit, are for the normal trigonometry functions like sine, cosine, tangent, the inverse ones, and the legendary arcus tangens with 2 arguments, because it does the same thing, but it takes 2 arguments. The example how it looks like, and maybe I can walk in closer. Whatever that thing is, I cast it to the radian angle. The underlying type is calculated. If it's any floating type, it remains. If it's not, it's double now. This is the resulting type. And whichever function it was called with, std func, it will call that function. So this thing here actually creates overrides of any function that you do. Now, what's cool, it creates a templated override. So all of a sudden, sine, cosine have a templated overrides for every single angle type I will ever create. And you only need to do this once. That's a cool thing. Did anybody manage to follow through with this, or should I explain more? In the next section, I can show this. So for example, the resulting type, if something is floating point, just return that. If not, give me a double, because I cannot calculate normal sine from an integer. I want to treat it as a double. From the normal ratio of normal degree to radian ratio, we can effectively just use this. This is to the third decimal, and in 99% of cases, this is precise enough. So I can maybe slide one thing back. So if I want to calculate the sine of something, I would just cast the angle I'm currently having into that same angle of, let's say if it was an integer, now it's a double, and convert it to a radian ratio. I will, in this case, depend completely on the conversion constructor and the STD ratio library to do all the dirty work for me. And this works perfectly for everything. We had, on the project, we actually had 3 angle measurement types depending on the equipment. Degrees, radians, and what they call an engineering unit. One is full circle, simply put. 2 is 2 full circles. And we had to convert between all 3 of these. Now, what's cool here is that one full circle is 360 degrees. So it converts 1 to 1. So that was quite cool and useful. The thing I didn't put here because it's not so pretty, and whoever wants to see it's in the code, is the absolute angle normalization to the interval. Is it 0 to 360 or minus 180 to 180, and how it works with every single type. Because in the code, I do not depend on the degrees. I just said I have a half an interval and I can move it left or right. Now, when I started servicing the angle guys, it turned out that the people working with normal dimensions also wanted to use other mathematical functions, for example, square and cubic roots. And this is an ugly thing to do because templates are not so cool with the calling squares and square roots and cubic roots on the template arguments. You simply cannot do that. So I cheated. This is what I did. So you will see here. So what does the square root do? It will create a new physical unit. It will invoke the actual square root on the value. It will divide every single dimension by 2, which is square root, and then it will call the magical thing a ratio square root of the factor argument. And the ratio square root is the ugliest, therefore the prettiest code I ever written. If it sees a 0, it's a 0. If it sees a 1, it's a 1. If it sees a 100, it's a 10. So I took the 10 most commonly used squared factors and also 10 most commonly used cubic factors and created a template overrides for all, and you can sue me for this. I'm quite proud. So I still haven't found the usage of the library where somebody said, oh, it doesn't compile. Like 360 or 3,600 is a common square of 60, and that's it. You know, it just works like that. Another thing that was commonly needed is that, in all actuality, my code doesn't cover the time as well as STD chrono. First and foremost, STD chrono deals with several clock types. You have monotonic, system time, monotonic, high precision, and so on and so on. And I have no idea what the clock is in the library. I just have time. And because, again, I was lazy, I converted two best functions ever. Here, they just convert any duration from STD chrono to the exact same time value in my library, and any time interval into the STD chrono duration. And this works perfectly, so in 99% of cases, you can use STD chrono for normal time measurement and whatnot, but then when you want to pull it in, you would literally just say unit cost of the STD chrono duration into the code and duration cost from my physical unit back into your code. So laziness is like a superpower here. That's actually, I have no idea how long it took. I guess some 25, 30 minutes. That would be like the whole presentation so far. So congratulations for sticking through. I would like to now take some questions from you. Yeah?
First of all, great talk. I have a question, actually.
I think the mic is off.
Okay. I actually have a question. Do you have an example of the API usage in action? Do you have an example of library usage in action?
Yeah, commercial projects I've been working on. I'm just
okay.
It's the NDA thing that I'm quite closed about. But yes, it is used in the real project, in the real applications.
Okay, I have another question. Do you support quaternions?
Sorry?
Do you support quaternions in the library?
I didn't have a need for those.
Okay.
So that's, again, like, this is how many of the features came in. Somebody just said, oh, have you tried complex numbers? I will, thank you. Do you have a quaternion implementation that I should, let's say, pull in here, or?
No.
Okay.
And the third question, as far as I've seen, you left, if you have an underlying integer type used for certain unit, are the implicit integer casts used, or do you have some handling of that?
It's actually not integer, it's whatever value type user sets.
Yeah, but if the user uses integers, it's left to the compiler with default integer promotion rules.
I use decal type for every arithmetic operation. So if somebody adds a short and an int, I give to the compiler via decal type to actually deduce the proper. If I add float and an integer, the compiler will give a type which is a float now.
Okay,
so
I see.
I left it completely to the C++ compiler defaults via decal type. It has been really, really useful in this regard. Otherwise, I would always enforce one or the other.
Okay, thank you.
Okay. Thank you for the questions, and thank you for quaternions. I now have a new hobby.
Yeah, you mentioned some well-known libraries that deal with physical units. How does your library compare to those?
Well, the first one that was actually the first one I found on Google when I was searching before we knew that before we learned that legally we cannot introduce a single line of third-party code was boost units. My problem there was one was that the dimensions are much more arbitrary in that case, and it's a lot less embedded friendly. For example, we have a huge love for integers, and the library is pretty much built around that. STD Boost, I would say, it was built much more with doubles and floats in mind. So that would be one, let's say, embedded critique. For the other library, and I forgot the gentleman's name, that's to my penalty, he's trying to push the official physical unit library for C++. That one is a work of art and is highly dependent on the really high-level latest and greatest C++ template features, which are simply not available on the projects I'm working on. So those would be the primary differences. I didn't, later on, I learned that there are quite a few physical unit hobby libraries, industrial libraries, and so on. I haven't compared with every single one of them. But in these two cases, I would still argue that for embedded projects, I think this is a better fit. That would be it. Anyone else? Anything actually unclear in the code, I'm quite willing to discuss why was something done, why something was done in that way or not some other, and so on. If there's anything that caught your eye, or that you didn't understand one bit of the code there, I'm quite happy to explain that as well.
Is there a place we can see the code?
Yes. Thanks for asking. Yes. There is a library. I finally pushed myself this year to actually publish it and to put some reasonable testing around. And the code was mostly lying around and being used left and right within the company. And thankfully, everybody was super cool about publishing it, clients as well. So yeah, I hope anybody else will make their own home appliance or some industrial appliance working with this as well. That would be like excellent. Yes.
Like units are often also used in gaming and those applications, but there you have coordinates and things like world coordinates and screen coordinates. Could this be extended to that use case as well?
Honestly, for screen coordinates and things like that, I think that the graphical libraries are perfect fit. I could imagine some physics engine or something like that written in C++ making use of these things and making the life of a developer using the physics library easier by using such a library, because they won't, I don't know, accidentally put liters instead of grams for the mass of an object which is thrown or something like that. I definitely wasn't focused that much on gaming or anything outside of embedded. I actually do not know for these physics engines if they have any sort of unit consistency layer, or you just put raw values and do with them. Does anybody actually have any experience with these? Okay.
So I have two questions. So one is regarding the templated square. Why not use the const expert?
But it is a const expert.
No, const expert function, not the template. You have it? It's supposed to
You cannot square root the actual STD ratio.
No, but so what you could create a const expert function which operates with int or doubles or whatever, and then just create a new STD ratio which has a value that is calculated by applying a const expert square function on the STD ratio coefficient that you extract. That sounds like
but that would actually mean that I would have to, so STD ratio has integers both up and down. And square rooting in this case might produce effectively floating point values. And if we come to that, we are probably in the deep pickle. So this is definitely a limit of the library. So this, and on the positive side, as I said, I didn't hit that wall yet.
No, of course, like the engineering trade-off is there. Like,
It's absolutely there. Like,
yeah, and the other comment is, so for the macro wrappers that you create, it's actually an interesting thing because so essentially you created the wrap a way of embedding the units into a type system of a value, and you chose to create macros for embedding the unit system to the functions, but you could have created like the same template mass of like having so you have a template tick that describes the units of a type, but you could have created a templated variatic thing that describes units of all arguments of functions, and then have a generic wrapper that could create a unitless function into a unit full function in a generic way.
if this is true, because this was my idea, so that I could just like wrap all of these. If there's something which is more elegant with less lines of code, I would gladly do it. I just didn't know how to do it, to be very honest. This was my engineering laziness again. So the idea is that, unfortunately, I would have to write the same piece of code for sine, cosine, and tangents here to do the overrides for each one of them.
No, so essentially, so if you step back and look at what you have done for the units, essentially we're like, hey, here's this thing that doesn't have this type in the physical sense, and I'm creating this constants per type, which represents a physical unit, and I'm assigning it to a value, so that you have a value with the physical unit. So that's essentially what's happening. And you could have the same kind of thinking for a function as well. So you have, so sine is a unitless function, it operates with ints, but you could have...
Well, it operates with radians.
So regarding the C++ type system, it operates with ints, and you want to, what you could do is have a separate type which describes what are the types of this function, you know, which you essentially did with this macro. So you essentially, what I'm trying to say is that instead of embedding it in a macro, as you did, you could have created a new type which has the generic description of all arguments, of all unit types of a non-type unit-typed function, and then create a generic applier of this generic type to untyped functions.
Since I really do not know how to do it, I would really invite you to go here and create a pull request. No, honestly, I like it, but to be quite honest, I killed the slideshow. 1 second. I would like to have it. The thing is, I don't know how. So, I would like to see it. And if the macros were a compromise, I wanted to do something more template-like, but this was the highest I could go. So, I'm absolutely accepted. Okay. Anything else? Cool then. I would thank you all for your attention, and that's it.